Hello everyone, welcome to the Deep Psychology Podcast. I'm your host, Ross Edwards, and today we're continuing on with our April series on the philosophy of science, and today we're diving into the bias towards models and explanations that exists within science. We're going to look at how this bias towards wanting to put names to things, to explain things, to model things, to give reasons for things, is actually very problematic, and how it constitutes a fundamental bias in science. Before we get into the main episode, I just want to say that I have new long-form episodes every Wednesday and snippets on Thursday, Sunday and Tuesday, always at 9 p.m. Central European Time, 8 p.m. UK time and 3 p.m. Eastern Time if you're in the States. Make sure to subscribe on Apple Podcasts or Spotify. And a quick mention that you can stay up to date with my latest episodes and projects via my newsletter. There's a link in the description to that. And you can also find my books there as well. So let's get into the heart of this episode. And this is just, again, it's building on the kind of theme that we've been exploring this month, which is on the philosophy of science. And really what I've been doing is exposing a lot of the biases that exist within science. And this is yet another one. It's the bias to model things, to explain everything, to find the explanation for things. And this, it's really quite obvious when you think of it. This underlies much of science, because really science is about making models. It's about making descriptive frameworks of reality, whether that's biology or chemistry or physics or neuroscience or any other scientific field. It's all about modeling things and finding explanations. And if you look at science, the theories, the laws, the discoveries, what are all these things? Think of Isaac Newton, think of Albert Einstein, Stephen Hawking, Richard Feynman, think of Maxwell and the laws of electromagnetism, and think of all the great scientific discoveries. What are all of these things? And you might say, well, they're discoveries about the workings of reality. They are works of genius that describe and reveal how our world works. Okay, what I want to propose is that these things are all actually models, and these people, these scientists, they're all model builders. Now, as I'll talk about much more as we go on here, the fact that they are models is both a blessing and a curse. And a lot of the things I'll be saying will be talking about how they are a curse, because that's really my focus this month. But it doesn't need to be a curse, but when we don't realize that these things are models, that's when we fall into trouble. So what is a model? Because if we're going to spend the next half an hour or 60 minutes talking about models, well, we must have to describe what a model is. So a model is just a set of observations or propositions that attempt to describe a phenomenon. It's very, very broad. And it doesn't have to necessarily even be a strictly scientific thing. Of course, in psychology, there are models. Even in spiritual practice, there are models, because if we are trying to describe a phenomenon like enlightenment, well, anything we use to describe it, or any way we attempt to describe how one reaches that, is a model. It's a set of observations or propositions. So you can think of a model as like a set of descriptions, or a set of ideas that describe something. Very, very broad. So for example, right, Einstein's laws of relativity, and even if you don't know what the laws of relativity are, in a mathematical sense, I'm sure you've heard of Einstein's laws of relativity because they're sort of famous scientific model. These laws are an attempt to explain how space and time work relative to objects moving at high speed. So the laws that Einstein came up with are a set of propositions about objects, about things moving at high speed, whether it's planets or a particle or any object. So it's about something. The laws are about something. They are a description of something. Now, this is where we start to even touch on one of the main flaws of models. And it's a really obvious limitation, but it's one that we often don't think about, especially scientists, and especially when you are in a rational stage of development. You often don't think about these things. You don't realize that this is the case. You just believe that laws are describing reality as it is. Here's the key thing about them. Well, here's one simple but very important critique, is that a model is always about a phenomenon. Therefore, by definition, it is not the phenomenon itself. So Einstein's laws of relativity are sets of descriptions, mathematical descriptions about how objects move. It's not the object moving itself, is it? Of course it's not, because we're talking about the laws of relativity. We're not talking about the objects themselves. You might say, well, we're describing the movement, and we can only do that through mathematics and physics. Well, yeah, but you're still saying I am describing the movement, and to describe is to make a description about something. You see, the keyword is about. It's about something. It's one thing related to another thing. It's something that is pointing to something else. So it's a law pointing to the movement or describing the movement. It's not the movement itself. It never is. By definition, Einstein's laws of relativity are essentially just equations on a piece of paper or a screen or in a book or wherever, right? It's not an object. It never is, and it never was. You see? So it's such an obvious thing, but it just shows you one of the main limitations is a model never actually describes a phenomenon accurately, because the only thing that can quote unquote describe something accurately is the phenomenon itself. And the phenomenon itself is not a model, it's just the phenomenon, right? And fundamentally, here's a deeper point, that phenomena in the world, fundamentally you cannot describe them, right? For example, right, you might, let's say that the device that you're listening to this on, you can think of that as a phenomenon. It's you're seeing it, you're holding it, you're interacting with it. It's a thing, it's an object, it's a phenomenon. It's like a phenomenon in our world, right? Or in your world. But listen, if I didn't know what a mobile phone was or a laptop was, or however you're listening to this, you could not describe that to me in a way such that I would be able to imagine what it is without other references. You see, you say, well, it's an iPhone, right? But if I already know what an iPhone is, then I've already seen it. I've already experienced it for myself. But without the reference to a prior experience, if you just say it's an iPhone, well, I've no idea what that is. And you describe what an iPhone is, and you describe the color and the shape and the size. There's only so much you can do, right? And that's a simple example, but it's the same as happening all the time in human life and all over the place. Try and describe what a banana tastes like. Try and describe what a sunset looks like. I used these examples last week. you can't, there comes a point where you can't describe them, and you inevitably have to just say, well, it tastes as it tastes, because I can't describe it to you. What I'm claiming is that all phenomena are actually like that, because there's just words just do not have the power to describe how phenomena are. And so clearly, models never describe reality. I mean, there are obviously better and worse ways to describe something. Like if you tell me a banana is the colour blue, maybe there are blue bananas in the world, but I've never seen one. If you tell me a banana is blue and you tell me it tastes like, I don't know, peanuts, well, you're not doing a very good job with your description. Obviously, there's better descriptions, but even the best descriptions fall short. There's always a gap between concepts and reality. And I hope this seems simple to you. It seems really simple and obvious to me. And I don't mean that to boast. I just mean because it's a fundamental limitation of concepts. It's just part of what a concept is. It's always about something else. It's never the thing itself. And this might seem trivial, but imagine not knowing the difference between the word banana and an actual banana. And you might believe, well, if someone just says the word banana to me, that means I'm eating a banana. It's the same as eating a banana. So if someone says the word banana 10 times, I've eaten 10 bananas, right? That's obviously not the case. So we need to be able to distinguish concept from reality at the most basic level. But listen, in science, this often does not happen. We often fail to distinguish concept from reality. We fail to distinguish a model from the reality of the thing. We say, well, the laws of relativity, this and that, and next thing, we pretend that they actually describe objects faithfully. And I'm not saying that they're wrong and they're not useful, but fundamentally they are limited. And it's not because Einstein wasn't a good physicist. It's just the nature of concepts and descriptions is that they can never describe things. Now listen, the whole of science, that is what it is. It's a conceptual system. So it never actually captures reality. And this, scientists do not understand this, and they do not recognize this because they fuse reality with concept all the time. And sometimes this might not be such a big problem, but in certain areas it's a huge problem. So let's get into the real key points of this episode today, the heart of it. Here's a really important thing. And this is very much related to models because it shows you how models are constructed and to what end. What we tend to assume as humans is that if we observe something, there has to be a cause to it. There has to be a first cause behind it. And then what we do is not only that, we assume that the first cause is more real than the phenomenon itself. If this sounds very abstract, we're going to look at an example, so just hold on. So for example, if we observe X to happen and we find out that Y causes it, then we say that X is happening because of Y, or Y is the cause of X. You see, this is a bias. It's biasing the cause over the effect. It's biasing what is observed before something happens to the phenomenon itself, right? This is fundamental to understanding how models work and what their limits are, because often the goal in scientific models is to model that first cause. Even Einstein was modeling a first cause because he was saying, well, an object moving at high speed, the mass changes and how it relates to time between observers. Listen, I'm a huge physics expert, but I know enough to tell you what I'm saying right now. The effects observed to that object, they are caused by space-time warping, or however he described it, right? So they are modeling the first cause, right? And obviously, you can calculate things directly about the mass and the velocity of that object, but fundamentally, it's basing everything on the fact that space and time aren't givens, right? So it's always like this like the step back is happening all the time. It's the phenomenon isn't enough in and of itself. We have to look for the cause behind it, right? So for example, let me give you a really concrete, obvious example. This is one we looked at last week when we were talking about why correlation is not explanation and the limitations this causes in brain science. But let's take the example of fear. So the way we usually look at fear is that fear is caused by something on a biological or neurological level. So let's say you get scared by a spider. Our usual explanation is, well, it's because there's brain activity, there's neurological activity, your amygdala is lighting up, and then there's a cascade of effects through the nervous system. So it's not just that we observe that there's simultaneous brain activity. What we often say is that we experience fear because of the brain activity, because of the thing that is behind the scenes. Notice that brain activity is invisible, and it's only detectable to brain imaging machinery and so on. To the human eye and to our ordinary perception, it is invisible. And science loves this stuff. Science loves invisible causes, invisible things that it can then say is the first cause, right? And then, or it's also behind the scenes, because looking at you, if you're scared, I can't see your brain activity. I can only see the effects of fear on you, right? That's all I can see. I can't see your brain activity. I can't even see your brain. So it's behind the scenes. And again, this is a huge bias in models. This is like, if you study science to any level, this is what science is doing all the time. It's putting the cause of things on things that we can't see, or that are behind the original phenomenon, right? With the example of fear, we could say, well, brain activity causes the fear. Therefore, if we just model brain activity and we understand brain activity, and we can change brain activity through drugs or through stimulating the brain regions, that's it. We've conquered fear forever. You see I don't know, if you can see the limitation of that. I really hope you do. That is a bias, you see, because as I spoke about last week in my episode last Wednesday on the 8th of April, you see that we never, drawing a causative relationship between the brain activity and fear is a bias. It's a scientific bias. All we actually have is the brain is activating, and at the same time we feel fear, or not at the same time necessarily, but there's a relationship between the two. We never actually observe causation, but it's a scientific bias to draw causation from that, to conclude that brain activity is causing us to be scared. And this is just happening in models all the time. So this is very useful, right? It's useful to look for first causes, and it's been hugely profitable. This bias towards first causes has probably been what's propelled science forward, but it's problematic. And demanding explanation for things, demanding an explanation for why do we feel fear? Why do we feel fear? That itself is a bias. That's an assumption. We assume that there is a cause, and we want to find out what that cause is. What if there isn't a cause? what if we actually cannot understand that fundamentally? Like, we might be able to superficially draw conclusions about brain activity and so on, but what if fundamentally we actually don't know how fear works? And I'm not saying we should accept ignorance and accept not having explanations as like a passive kind of stance, or as like a kind of resignation. What I'm saying is, when you open that yourself to the possibility and you see that fundamentally what we're looking for is explanation, and you ask, well, is that the right question to ask? Is that a bias? Is that actually creating more problems than it's solving? Then you can say, well, it opens you up. And then any subsequent reasons you might give for why we feel fear, for example, this can apply to anything, but just for example, those subsequent conclusions are likely to be more they're better reasoned and less subject to bias and less subject to like scientific dogma and typically scientific ways of interpreting things. And also, just because we might reject an explanation for something, it doesn't mean we need to replace it with another thing. We might find that maybe the brain doesn't actually cause fear, and then of course we ask, well, what does cause fear? And that's our natural instinct, but again, what if we're jumping the gun? What if we need to really look at deeper assumptions about how life works before we start basing ourselves on other assumptions that might themselves be erroneous, trying to find an answer? Is to sit back and consider more carefully what are we asking, why are we asking it, right? This is real inquiry. You see, putting things to a first cause, like an invisible first cause, like brain activity, that is not real inquiry. That is working within the scientific paradigm and applying it to new phenomena, and then immediately assuming that those new phenomena can be understood through that paradigm. But what if they can't? And I'm not saying that that's the only thing we need to do to inquire, but at least we're seeing those assumptions in that paradigm, right? So let's get into the main critiques of models and explanations here. For one thing, the desire, you see that the act of building a model already introduces bias. For example, models impose variables on things. And when we impose variables, usually we're trying to impose independent variables for so many reasons. And again, you see that this is the more we conceptualize things, the further we are getting away from reality, the further we're getting away from the actual phenomenon itself, and the further removed we are from actually seeing things as they are, right? And again, our variables and our concepts might be useful, but what if they're not? What if we're actually just tying ourselves in knots here? And again, variables are a very subjective thing, because you choose variables according to what you think is important. One variable might be, brain activity. One variable might be, what is the thing the person is getting scared of? Another variable might be, how much time are they exposed to it for? You see, it's breaking things down into very kind of rigid and chunky categories. You see, and again, that might be useful, but again, it might be a huge bias and a result of our own limited thinking. As I've said, models tend to favor hidden mechanisms. Let me explain another side of this that I haven't looked at yet. What you'll notice if you study science is it's very, very hesitant to assign reality to anything. It's very reluctant to say, this thing stands on its own and it doesn't need an explanation behind it. And it's not only that, it tends to assign reality to parts of things rather than wholes of things. For example, right? Science has a hard time assigning reality to just a human being. What science will tend to do is it'll say, well, what is a human being? Oh, well, a human being is just cells. Really, when we break it down, that's all it is. The skin is made of cells, the face is made of cells, the eyes are made of cells, the brain is made of cells, even the bones are made of cells, you see. And then they'll go another step and you say, well, what are the cells made of? We've spoken about the human being, and a human being, it seems like this, elaborate, complex, almost really too complicated to understand, this thing. When we can break it down into cells. But what about a cell? A cell, if you look under a microscope at a cell, looks like this amazingly complex thing. But, well, if we can do that with a human, why not do it with a cell? Because a cell isn't as complicated as a human. So let's break a cell down. And we find its molecules of all kinds. And then, well, what are molecules? Oh, well, they're all just, fundamentally, molecules are just constituted from the periodic table of elements. And then what we've done is we've broken the human down into cells, we've broken down into molecules, and we've broken down into the elements, the chemical elements. And we'd say, well, the human being really is just the chemical elements. And then we can say, well, what is an element? What is an atom? What is a carbon atom? What is a carbon atom? And we look at that, and what we've discovered in the last kind of 100 years of physics is atoms are mostly nothing, nothing at all, not even air, nothing. Not like how what's inside a balloon is really nothing. No, what's inside a balloon is air. The actual, the substance of a carbon atom is mostly nothing. The volume of a carbon atom is mostly just nothingness. So we can say, well, the human being is just nothingness, because the human being is just cells, and then the cells are just molecules, and the molecules are just composed of different atoms, and all atoms are mostly empty space. So the human is mostly empty space. Now, on one level that is true, but on another level, clearly a human is not just empty space. I mean, come on. Even the most rigid scientist doesn't relate to other people, and certainly not to themselves, as though they were just empty space. They don't. How would you relate to someone if you really genuinely believed they were empty space? You really felt down to the marrow of your bones that they were empty space? Well, you probably wouldn't speak to them, you probably wouldn't love them, you probably wouldn't interact with them, because you don't sit and talk to the air inside a balloon, do you? Well, you might, but most people don't. You see that that's the gap, when we reduce things down, we think, oh, well, we're analysing, we're parsing it, we're understanding it more deeply, we're getting to the constituent elements, and therefore, because we're getting to the constituent elements, then we're understanding the human, and we have a good model of the human. But no, because your fucking model is that the human is empty space. That's what it basically boils down to. So clearly that's not a good model, because you don't, as a scientist, you don't relate to other people as though they're empty space. You don't. So that's that's another problem, the problem between the gap between concept and reality, which is spoken about. But it's the problem of thinking that because we look at the hidden, what is hidden within things. Cells are hidden within the human, and then molecules are hidden within the cell, and then atoms are hidden within the molecule, and so on. We think that we're understanding the thing better, but actually no, we're just becoming more and more removed from the actual thing itself. This is exactly what I'm talking about. The scientist will not assign reality to a human. It doesn't. It always wants to break it down. It wants to break the human down into atoms. But there's a huge problem with this, and it's so like glaringly obvious.